Okay. Hello everyone. Welcome to today's quantum spacetime seminar. We are very happy to have Aninda Sinha from IISc Bangalore, who will tell us about dispersion relations and knot theory. Over to you, Aninda.
Thank you very much for the invitation. So I would have very much liked to be in person, irrespective of Gautam's comments. But yeah, I would have really have loved to have been there physically. So I'm going to tell you about dispersion relations and knot theory, and this is something I would like you to ask a lot of questions because I literally have 10 written slides so that the talk would be as interactive as possible. So this is an understanding, or this is something that is evolving over the last couple of years. I'm quite confident that I have not yet reached a state which could be called a complete understanding of this problem as yet. So this is based on a paper that I put out in April, end of April. And so I should actually point out that there is a version 3 which I think is more complete. It has got a quantum mechanical picture, which is, in my opinion, going to be a very interesting one. But it builds on something that we have been working on here in IISc for almost the last 2 years or so. Actually, more than that, because there is a history. The way that my interest in this problem began was to understand the so-called Polyakov bootstrap, which I'll have nothing to say about. So there are a bunch of papers. So anybody who wants to follow up on the kind of things that I'm going to talk about is going to be at a sort of level which I will work through as much as possible. But the background builds on something that I did with my graduate student Ahmadullah Zayed, who might be there in the audience, which is the crossing symmetric dispersion relation. And there was a similar story that was there in Mellin space, which is relevant for CFT, which was developed with Rajesh Gopakumar and Ahmadullah, which I will not mention, but then the conclusions are going to be quite similar so far as that story is concerned. And then there was a bunch of papers. So the motivation was to try and understand these so-called two-sided bounds on Wilson coefficients. Wilson coefficients are basically, you have a 2-to-2 scattering amplitude and you do a Taylor expansion of that. And then those Taylor expansions are called Wilson coefficients. And the ratio of Wilson coefficients satisfy two-sided bounds. These are could have been anticipated from the success of the Wilsonian paradigm, but mathematically these weren't established until maybe a couple of years back. The first paper on this topic, which actually made this observation, at least the published paper which made first this observation concrete, was a paper by Andrew Tolley and collaborators. But this was an observation that was made by Nima Arkani Hamed and collaborators before they put their paper out, which is called the EFT hedron. And then there were further follow-up papers by Simon, Karen, Holt, and others. So we wanted to understand this origin of the two-sided bounds in our own way using this crossing symmetric dispersion relation. And so there was a couple of papers which was written with my graduate student Parthiv Haldar and Ahmadullah Zayed, which was based on the famous Bieber-Bach conjecture in mathematics. And our claim was that the two-sided bounds that we get on the Wilson coefficients are nothing but a restatement of the Bieber-Bach conjecture. And then we wrote a paper with Prashant Raman, who is a postdoc at IISc, which I believe gets the right ingredients, which is based on geometric function theory. I will briefly mention some of these things, as much as I will need. So these three papers, let me just point out. So these three papers strictly dealt with 2-to-2 scattering of scalar particles with arbitrary exchanges. And in this paper, we generalized this to spinning external particles. This was written in collaboration with Shubham Datta Chaudhary, who you all know because he was a postdoc in TIFR, Kaushik Ghosh, who was my previous graduate student, Parthiv Haldar, who's technically still my graduate student, but he's going to graduate this year, and Prashant Raman. So let's get going with the motivation. I would really encourage that you stop to clarify motivation, clarify simple things, because I want this to be as interactive as possible. So as I mentioned, one of the reasons why we wanted to study this problem was to constrain the space of effective field theories. And by constraining the space of effective field theories, I have in mind a very specific class of terms, non-renormalizable terms that we would add to the Lagrangian, which have 4 fields, because we are going to study 2-to-2 scattering. So using 2-to-2 scattering, we will not be able to constrain anything apart from these 4 field terms. So we want to understand these dispersive constraints on specific terms in effective field theories. And that's an interesting problem because this has not been done, so we don't really know whether we have the optimum set of constraints so far. And one of the things is that at least so far as 2-to-2 scattering is concerned, is there a way that we could classify these constraints in a manner that is similar in spirit to classifying conformal field theories? And most of this talk I will focus on gap theories. So in the complex S-plane, I will assume that there are these S-channel cuts and U-channel cuts. I will not require there to be no poles. I mean, the case with poles can be generalized, but for most of the talk, just for concreteness, not because of any technicalities, I will focus on this picture. And this is a favorite picture for axiomatic quantum field theorists who studied these problems in the 1960s. So they were interested at that point of time on pion scattering, and by looking at this problem, as you all know, by looking at crossing symmetry and these kind of constraints, is what led to the origin of string theory. Okay, so let me just summarize some key findings before going into the introduction and background and so on. So there are a couple of key findings. The first one is that we will see that when we try to constrain the space of effective field theories, there will appear quite naturally specific kinds of knot polynomials in discussing these EFT bounds. So here is a picture. So let me explain what the various axes are. So the y-axis here is a specific combination of the derivative of the amplitude. So we are taking the second derivative of the amplitude, normalizing it by the first derivative, and taking the modulus. So that is the y-axis. I will explain more specifically what the derivative is with respect to later on. It is with respect to the crossing symmetric variable. I will introduce that in a bit. And we are asking what is the magnitude of this object? And the plots have, there are various plots, so let me just go over them one by one. So the red guy is what would appear in from phi cubed tree-level amplitude. And this phi cubed tree-level amplitude is something that I will spend quite a bit of time. So it is the simplest amplitude that you can think of. So this red guy actually behaves like this. So let me trace it out like this, and then it joins up with the blue line. Here it joins up with the blue line. The black line is phi-4 theory at one loop, because phi-4 theory contact term is trivial, so you have to go to one loop to get something interesting. So that is the one loop line. The x-axis, I should have said this earlier, but this x-axis here is like the Mandelstam t variable. So I have put a quotation mark because t I'm going to use in multiple contexts in my talk. So in this case, you can think of A as a proxy for t. These dots are what come from bootstrap numerics. So you can do pion S-matrix bootstrap, so building on ideas by Penedones and collaborators. So this is similar in spirit to the kind of talk that you heard from Pedro Vieira last year, where he used the S-matrix bootstrap to find string theory at one of the corners of the allowed space.
So I have a question.
Yes. Is there a question? Yes, from that. Yes.
Yeah. So phi-4 theory at tree level, what sort of curve would that give?
Yeah. So that's just a constant. So that would be a trivial some line somewhere. Yeah. It's just a constant. It's a contact interaction. Yeah.
Aninda, this bootstrap, is it of the dual nature or the primal nature?
This is the primal.
Okay.
Yeah. This is the primal nature. Yeah.
Thank you.
Sorry, I missed something. This derivative are with respect to what?
Yes, I will specify that. So I have not mentioned, it is with respect to a crossing symmetric variable. So because I've not introduced the crossing symmetric variable as yet, that's why I did not mention what it is.
Aninda, one more question. So you have assumed absence of gravity, or
yes. So I have assumed here in the plot that I'm showing here, I don't have any massless particles.
Okay.
Yeah.
Thank you.
Okay. And one question would be that, so you can see that there is some kind of envelope so far as the numerics is concerned. So can we analytically derive what is the bounding curve in this picture? And I will show you that this bounding curve is given by this blue solid line. And this blue solid line is going to be specifically the Alexander polynomial for the trefoil knot. And I will derive all that for you in this talk. This black.
One more question.
Yes.
When you say there are no massless particles, can the mass be arbitrarily low, or you put some bound on the?
I have normalized everything with respect to the mass. So.
So mass is 1 in this.
Yeah. So mass is 1. Yeah.
Okay. Okay. Thank you.
Sorry, Anindya, just say once more, what is the significance of the blue curve?
Oh, yes. So the blue curve is the bounding curve, which we can derive analytically, which is going to tell us that in the theory space, there will be no points that you will get above this line.
Oh, I see.
Okay, so the blue curve is the theory space bound, and the theory space bound is given by an Alexander polynomial for the trefoil knot. So I'll give you the background for all this in a bit.
Okay.
Sorry, Aninda, you just made a dual statement that you should not find a point on the upper above side.
Yes, I mean, so the primal thing is that it converges. So I know that I made a dual statement, but the primal problem is that you won't be able to. So as you increase the number of variables in your problem, it sort of converges to a line. So it could converge from above or converge from below. But the statement is that as you increase the number of parameters in your space, it will converge.
Okay.
Yeah.
But it is still true that all the theory cannot appear above this blue.
Yes. So the blue line is actually a strict upper bound. I will derive that for you.
And can you saturate this upper bound in any theory?
That's a very interesting question. The answer is I don't know. Yeah. So I can tell you some extremal theories, but I don't know if there is a single theory which actually lives on this.
Okay, thank you.
So this function which you've taken on the y-axis is specifically for this Alexander polynomial of trefoil, right? If you had taken a different function, maybe it's some other knot.
Yes. No, that is true. Yeah. So it's basically a combination of the derivatives of the amplitude. So there are two derivatives of the amplitude here. So you will see why I chose these combinations. Yeah.
And is there any significance that the physical theories you have curve dipping down to 0 and coming up?
Yeah, I need to think about this. I don't know why the physical theories. I think they changed sign, and the physical theory is actually because of the fact that I put a mod sign. It's the fact that the physical theories changed sign that's why. Yeah.
I have a related question.
Yeah.
When you consider the 541 loop, and you make an expansion in say higher, if you make an OP expansion, or say the sort of LSZ sort of expansion, wouldn't that give rise to something like the bootstrap numerics thing?
Not sure I followed the question. Can you repeat that, please?
If you have the 541 loop thing,
yes,
and you make a sort of an LSZ expansion,
okay.
So then you would have various masses, various particles of you would have various particles of various masses contributing to the tree level exchanges instead of the
but that will be like the Wilson coefficients, though there will be fixed, so you won't get a theory. You'll get some line.
The Wilson coefficient will be fixed, but I'm just wondering why you should get the sort of 541 loop in this particular curve instead of something which is more nearer to the bootstrap numerics.
Okay. Now I understand your question. So you're asking that why is 5.4 not closer to the bootstrap numerics? I'm not sure. I mean, the phi cubed is close to the bootstrap numerics, and you will understand when I go through the phi cubed, you will understand why. So the phi cubed actually saturates, it actually overlaps with the blue line. Yeah, phi 4
Yeah,
and,
but the phi cubed is just one particular particle being exchanged.
yeah.
That would have been less coincident with the bootstrap numerics than the phi 4 theory, for one loop theory, right?
No, phi 4 at one loop, you still have one parameter, which I have normalized to 1. So you'll get arc tan tangents in your answer, and then you're doing a low energy expansion of that answer.
Why would you get one parameter? Because if you have, say, the...
No, after you renormalize, yeah, the renormalized answer depends only on the renormalized mass. And there is lambda square. Lambda square is sitting outside, but since I've taken ratios, the lambda square cancels out.
No, the loop inside, the loop inside, which would contribute to the scattering, it would just be one loop with two legs coming out on both sides, right?
Yes, yes.
So that sort of loop, you can't, I don't think that sort of loop would have a sort of expansion in masses or something, or...
No, it does. I mean, so you can look at, so the explicit answer can be found in Peskin and Schroeder. So the normalized answer actually looks like the crossing symmetric version of arc tangents in terms of S1, S2, and S3, which are the three crossing symmetric variables, which are shifted. So, and then you can do a low energy expansion around S1, S2, S3 equal to 0. So you will start getting crossing symmetric polynomials whose coefficients are going to be the Wilson coefficients.
Yeah. Okay, maybe we will continue.
Yeah. Yeah, I can show you the explicit formula maybe at the end of the talk. Okay. Okay,
so the y-axis derivatives are at 0?
Yes, the y-axis derivatives. So I have to specify what the derivatives are. So I will tell you, I will define the derivatives carefully because
low energy coefficients basically.
Yes, they are going to be low energy coefficients, made of the low energy coefficients, indeed, yes. Okay, so that was the first lesson. So hopefully I will be able to derive everything for you. And the second lesson is that we can rewrite this 2 to 2 scattering amplitudes in terms of the thermal expectation value of a Q deformed harmonic oscillator. And this is a rather strange sentence, and you'll be scratching your head. I mean, was this expected? No, this was not expected, but I will show that indeed you can do it. And somehow the thermal expectation value of a Q deformed harmonic oscillator comes into the game. And I will tell you what this Q deformed harmonic oscillator is. And the slogan here is that the amplitude is equal to partition function times Q average. So Q is the deformation parameter. And in a very precise sense, Q is also the knot polynomial parameter. So you're actually averaging of the knot polynomial parameter, or you can think of this as averaging over the Q parameter. And so the amplitude is the partition function times this Q average of a 2-point function. So A dagger A is like a 2-point function, the expectation value, the thermal expectation value in this deformed theory. So Q here generates a knot parameter. So I will tell you what this is. And this 2-point function actually is a generating function for the knot polynomial. So, so that is the second lesson, which will follow from this picture of this Q deformed harmonic oscillator.
Okay. Aninda, maybe you will explain it later, but I just wanted to check. So you have the S plus T plus U equal to 4 in this case, right?
Yes, yes.
So the low energy means what exactly?
So around the crossing symmetric point. So in my variables, I'm expanding always around. So I've written, yeah.
So that 4/3, is it? I mean,
yeah, exactly. Yeah.
I see. Okay.
Yeah.
Okay. Thank you. So that requires complex momentum somehow. Is that right?
Yes. So indeed. So you will see that I will require to think in terms of complex angles.
Okay.
Yeah. Okay. So so there are two main lessons. One of them is I'll be able to derive this bounding curve in terms of knot polynomials, and the second lesson is that I'll be able to find a map which tells me that the amplitude can be thought of as the thermal expectation value in a Q deformed harmonic oscillator. And this Q deformed harmonic oscillator actually plays a very important role. It appears in many theories. So for example, It it does appear in the discussion of knot theory. It appears in conformal field theory. So for example, rational conformal field theory. It appears in the discussion of two-dimensional string theory. 2D string theory, and so it actually appears in a lot of places, which may not be familiar to all of you. Okay, so let's get going with some math background. So I'm doing quite remarkably badly with time, but doesn't matter. So, and here Rama is there in the audience. So if I make any goof up with any of my statements, Rama, please correct me. So I will, I will give you a brief background of what I need. Of course, knot theory is a very vast topic, and I will require only some small part of it. So what are knots? So knots are what you would mentally picture. So there's a mathematical definition of knot, that it is a map from S1 to R3 with no self-intersections. So for example, the simplest knot is what is called an unknot. So there is nothing that is knotting. So here is what is called the trefoil knot. So you can project the trefoil knot onto a plane, but it literally lives in 3 dimensions. So here it's a nice picture that I got from the internet. You can see that there is one piece of the rope that passes on top of another piece, and then there is another piece that goes below this piece, and so on. So there are crossings here. These are called crossings. This knot here is what is called the trefoil knot, and this is what the knot that actually forms this bounding curve. I will mainly require knots like the trefoil knot, which are called torus knots, and these torus knots are labeled by 2 co-prime integers, p and q. So in the trefoil case, it is labeled by 2 and 3. So 2 actually tells me how many times the rope or the string that you want wraps the longitude, and 3 tells me how many times it wraps the meridian. So the 3-dimensional picture it probably has more, I mean, you will be able to make out what's going on by looking at the 3-dimensional picture. So here you start, it goes along, goes below, and then comes around 1 time, and then goes again here, and then comes back, comes around twice. So that is the 2 here. Whereas the short, this short axis, it wraps around thrice, once, twice, thrice. Now, as I said, in this discussion of dispersion relations, I will focus on only torus knots, because those are the ones that come naturally. They are labeled by 2 co-prime integers, p and q. And on top of this, we will be only interested in a special kind of torus knots where p is 2, and so q has to be 2n plus 1. So if p is 2, q has to be co-prime, so it has to be an odd number. Now, in knot theory, to distinguish knots, we use knot polynomials. So one famous knot polynomial that you may have heard of is the Jones polynomial, because Wheaton wrote this very famous paper called Quantum Field Theory and the Jones polynomial. And a lot of work has been done in extracting physics out of this via the Chern-Simons field theory connection. In this talk, I will only need the oldest knot polynomial, which is called the Alexander polynomial. And the Alexander polynomial was sort of, what is the right word? So invented by J.W. Alexander in around 1923. And J.W. Alexander actually was a mathematician in the Institute for Advanced Study in Princeton. And he sort of, what one could say, was one of the founders of this area of mathematics called geometric function theory. The specific area of the geometric function theory called univalent functions. And also he was the person who first gave us the first knot polynomial, which is called the Alexander polynomial. And until the invention of Jones polynomial, it was the only knot polynomial that was known. And so let's write down some examples of knot polynomials. What do they look like? So the trefoil knot, which is the knot that I showed you already, looks like this. So it's there is a knot polynomial parameter t. Now this is where there is a sort of a conceptual gap. between mathematics and the pictorial intuition that you would have thought. So the conceptual gap is that here we are talking about knots, and we said that there are these beautiful three-dimensional pictures, and we're going to distinguish various knots using these knot polynomials. So you might have intuitively thought that there must be a connection between this parameter t and exactly how this knot goes around in the three-dimensional space. Now, unfortunately, there is no such simple connection to the best of my knowledge, and Rama, you should correct me if I'm wrong.
Yeah, I'm listening.
Yeah. So
Another question.
Yes.
Surely the t parameters are different in the two cases, right? I mean, they can't be the same parameter.
Different in the two cases means what? So it's just a
But,
parameter.
I mean,
Yeah,
no,
but it is the same parameter. It will give you, so if you put in a number, it will give you two different numbers for the knot. So in that sense, I'll get two different answers for the two different knots.
But if you have a different polynomial,
Yeah.
if you can have different polynomials, shouldn't the parameters of the polynomial be related to each other in some sense?
I mean, when I'm saying that I'm going to use different knot polynomials to distinguish the two knots, that parameter is the same by definition. Right? I mean, otherwise, how will I use the polynomial to distinguish two knots? So I'm saying that if I have a knot which is called the pentafoil knot, and if I have this trefoil knot.
Oh, okay.
Then,
so I thought this 2, 3 indicated that you are just showing the trefoil knot again and again. It's not correct.
No. So sorry. Maybe my handwriting is not.
Oh, this is 2, 5. Okay.
This is the pentafoil knot.
Okay.
Aninda, a bit tangential question. This is also some Chern-Simons something?
You're asking whether there's a Chern-Simons description of these Alexander polynomials.
Yes.
So no.
You can take it as SUN Chern-Simons, and n equal to 2 is Jones, and n equal to 1, n equal to 0. In that limit, you can start getting the Alexander polynomials. So there are ways of doing it.
So you analytically continue in n to 0 or 1?
That's right.
Okay.
That's right. So the recursion relation is q to the n times overcrossing minus q to the minus n over undercrossing equal to the t variable times no crossing, right? So if you put n equal to 0, you will get the Alexander recursion.
Okay. Got it. Thanks.
Otherwise, if you put n equal to 2, then you will get the Jones recursion.
Okay. Thank you.
Okay. Yeah. So it's not meaningful to call n equal to 0, but you can do this on the recursion relation equation.
Yeah.
Yeah, continue.
Yeah. Okay, so as I said that I will require two 2n plus 1 kind of knots. And there is a simple closed form expression for the 2n plus 1 kind of knot, which is just given by this. So if we had 2, 1 instead of 2, 3, so 2, 3 is the trefoil, this is the pentafoil, and so on. It would be just be 1. So the 2, 1, which is the unknot, is just 1. The Alexander polynomial, of course, has other properties. So for example, if you set the value of the knot parameter to be 1, then it becomes 1. So that's how these have been defined. And also there is something called the knot determinant, which is a topological invariant, which is obtained by setting t to be minus 1 in the Alexander polynomials. And if you set t equal to minus 1, you get 2n plus 1. And this is also equal to the crossing number, the number of times you cross. So for example, here you get 3. So indeed, this is 2n plus 1. So 3 is the number of crossings in this particular knot. That's about what I will, the information that I will need so far as okay. So there is another piece of mathematics that I will need, which is actually very important. So there is another piece of important piece of mathematics that I will need, which I learned from a couple of papers by a couple of Ukrainian physicists / mathematicians called Gavrilik and Pavliuk, which relates the Alexander polynomial, that I am interested in, to the Chebyshev polynomial. So these are Chebyshev polynomials of the second kind. And I'm throwing a bit of mathematics at you, and it might not be clear why I need this, but just remember that there's a connection with Chebyshev polynomials. The Alexander polynomial is related to the difference of two successive Chebyshev polynomials. And these Chebyshev
So
polynomials.
T and Q are related?
Yes. So the Q, you mean the Q parameter that I introduced earlier?
Yeah, the Q number.
Yeah, Q number. It is related. So Q is equal to T. Yeah. So I should tell you, if I use Q at any point, you just replace it mentally by T. It's not obvious why that should be true, but in my story it is.
And this T has nothing to do with Mandelstam variable, right?
This T is nothing to do with Mandelstam variables. I will give you the relation between T and the physical quantities when I discuss the crossing symmetric dispersion relation.
So this Chebyshev polynomial is a polynomial of nth order?
Yes, it's so for example here I've given you the first few Chebyshev polynomials. So it's a degree 2. So UN is a degree n polynomial in X. Okay. And so the statement is that the Alexander polynomial of these torus knots is related to the differences between these Chebyshev polynomials under the identification that 2x is equal to T plus 1 by T.
Sorry, what did you say about the Q? Because there is no Q in this equation.
Oh yeah. So here actually Rama was pointing out this this observation. So this is actually so this Chebyshev polynomials of the second kind are related to something called Q numbers. I will tell you what Q numbers are. So they are generalizations of ordinary numbers, and they will enter the story via this Q deformed harmonic oscillator.
Okay, fine. Thanks.
Okay. So the final piece that I will need, so far as the knot background knot mathematics is concerned, is that it is known, and you can see Wikipedia, that the generating function of the Chebyshev polynomials of the second kind are incredibly simple. You have encountered this before. So for example, if this was raised to some power alpha, this would simply be the generating function of the Gegenbauer polynomials. When alpha is equal to 1, this becomes the generating function of the Chebyshev polynomials of the second kind. So that is something that you will need, and you will see that this actually enters. So this is going to be related to the kernel in the dispersion relation. So that is how the Chebyshev polynomials will play out.
It's ZX Z.
This is x times z, and this is z square.
The coefficient is 2.
This is 2. Sorry, yes. This is 2. 2, 2, 2. Sorry. Yeah, sorry. Yeah, z, the way that I write z to distinguish from 2 or anything else has a cut. And so another simple observation that you can make is because of this relation, you get a very simple generating function of the Alexander polynomials, which is you simply take this function and multiply by 1 minus z. And then this becomes the generating function of the Alexander polynomials. So just remember the structure. It has this 1 minus z on top, 1 minus 2xz plus z square. And that can be expanded in terms of the Alexander polynomials times z to the power n. Okay. And then I promise that the background of mathematical background will be another just 2 minutes, and that's it. So the final.
So essentially, you will just get some similar form 1 minus z by 1 minus 2xz plus z square in the dispersion relation, right?
Yes, exactly. So that's what is going to happen.
Okay.
Exactly. Okay, so the final piece that I will require, and that is to connect up with the Bieberbach Rogozhinsky, so this geometric function theory story that we developed last year, is just a few lines about the Taylor expansion coefficients of a certain class of functions. So you might have thought that we are interested in bounding Wilson coefficients. So from the mathematical side, what can we use? So one thing that we can use is what is called a typically real function or a Herglotz function. So this is also called a Herglotz function. So f of z is a typically real function or a Herglotz function if it satisfies this condition: the imaginary part of f of z times the imaginary part of z is bigger than 0. And further, if fz is regular inside the unit disk, so for example, if there are no poles, if there was gravity in the story, there would be actually a 1 over z pole at the center, and we could handle that, but then it will require a modification of these typically real functions. you will require meromorphic typically real functions. Those also mathematicians have studied, but I don't have time to go into all that. So if f of z is regular inside the unit disk, and you write it like this, so mentally you can think of these as the Wilson coefficients in the scattering amplitude story, then these satisfy two-sided bounds. So they are bounded like this. So an is bounded, upper bounded by n and lower bounded by minus n if n is even, and kappa n, there is some kappa n actually is the maximum of minus sine n theta by sine theta. You can work this out very easily numerically. If n is odd, then you have these kind of two-sided bounds. So these are called the Bieber-Bach.
In general, would it be a convergent series? Because if it's in general, would it be a convergent series?
No, so it is. All that I need is that it is analytic inside the unit disk. So there could be some singularities that are lying on the boundary of the unit disk or somewhere outside. Yeah. So the radius of convergence is set by that. Okay. And mathematicians know that these typically real functions admit something called a Robertson representation. And in fact, there is a connection with physics as well, because the way that this Robertson representation worked out is due to some connection that was pointed out first by Wigner in 1951, I suppose. So, but the statement is that if f of z is a typically real function which is regular inside the unit disk, then it admits a representation of this kind. So just quickly, so there is a probabilistic measure factor where I'm integrating over psi, and then there is a kernel which looks like z over z square minus 2 psi z plus 1. And of course, now you begin to see that there is a connection with whatever I have been saying so far. So this is the generating function of the Chebyshев polynomials, and as a result, they will also be connected with Alexander polynomials. So any questions regarding the maths background? Because now I'm going to go slow and work out phi cube theory.
Sorry, Aninda.
Yes.
What is the definition again of the typically real function?
Yes, the typically real function is this. So function is supposed to be typically real if the imaginary part of f of z times the imaginary part of z is greater than 0.
Okay.
So this is true. So this actually gives you a definite sign above in the upper half plane and a definite sign in the lower half plane.
Okay. So it needs to meet this condition everywhere in the complex plane, and then it needs to be regular inside the unit disk. Then these properties follow. Huh?
Yes.
Okay. Thank you.
I have a question. Hello.
Yes.
Can you hear me?
Yes. Carry on.
So, are knots going to figure in a more, important sense than just the fact that you're getting the Alexander polynomials? Is the property of knots going to figure in an important way?
Okay, so that will become clear when I discuss this. Now I'm going to discuss scattering, so it'll become clear maybe after I make the connection. So there will be some crucial ingredients of knots which will become transparent, but so ask me the question after I present this story.
Okay.
Hi, this statement about this Robertson representation is that like you take psi with any bounded psi within one, but any distribution will give you some appropriate f.
Yes, so there is some psi min. The way that normalization works is psi is between -1 to +1, but it could be from psi min to psi max. So it's some bounded interval.
Okay, and also in the generating functional expression, the x is the analog of the psi, right?
Yes, sorry. Yeah, I could have called it psi.
And the x was defined as some t plus 1 by t or something, which is bounded from below, or like.
Right. Yes, right. So
the bound seems to be working the other way, no?
No, I will make I will give you the dictionary very precisely in a bit. So what will happen is that in order to write this representation, I will require 2 psi or 2x, whatever you want to call it. So psi should be the mod of psi should be less than 1. And you will see that actually corresponds to q being a phase. So that will translate into t is being e to the power I theta.
Okay, thanks.
Sorry, what is psi? What is
psi? Is what is entering the
okay.
This generating function. Yeah.
Aninda, one somewhat tangential question. This Robertson representation, is there something to be said for functions which are given like so, but with some power of the denominator?
Yes. So you want to ask whether we can say something about 1 over z?
No. I mean, 1 over z square minus 2 psi z plus 1 whole to the power alpha.
Yeah. Oh, acha. Okay. So something like the generating function of the
general Gegenbauer
of the Gegenbauer. Yeah. That's a very good question. So we have been asking some mathematicians the answer to this. So in fact, we don't have a complete answer. Yeah, it's a good question. So whether you can have typically real functions with raised to some power alpha. Okay. So I don't know what the general kernel is.
Okay.
Any other questions?
Sorry, just one more question. This typically real functions, can you give some intuition as to why it's called typically real?
Yeah, mathematicians. Yeah, unfortunately, mathematicians. I think. Yeah, okay. So one reason why they are called typically real is because you can actually show that these ANs have to be real. Okay. So in geometric function theory, when you do a Taylor expansion coefficient, Taylor expansion like that, these ANs could be in general complex. But if you look at this particular condition and the regularity inside the unit disk, you will conclude that they have to be these ANs have to be real.
I see. So another kind of abstract question: what is geometric about geometric function theory?
Oh, these are these are like conformal maps. So you can think of these as maps from the complex plane to inside the unit disk or vice versa.
Okay, thanks.
I have another question. Can you go up? So you had 1 minus z. So where is the 1 here in fz?
1 minus z. Yes. So yeah. So you're asking how I.
Yeah, in integral representation for fz.
Yes.
You just have z.
Yes.
So the Gegenbauer polynomial expand in the generating function for the.
Yeah. So here I could trivially multiply by z, and this will become just z plus 1. So so that part is that part is not. I mean, it's just the generating function of un. Yeah.
But then you don't get the generating function for the Alexander polynomials. You just get.
Yes. So that is why you require to. So you remember, this is kind of an important point, that you remember that I had to take linear combination of the derivatives here. So what will happen is that because of this point, I have to take difference between derivatives of the amplitude to get a particular knot polynomial.
Okay.
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 Okay. So actually, I wanted to go slow at this point because yes.
If you don't take that combination, you will still get some polynomial, right?
Yes, you will get the Chebyshev polynomial of the second kind. Yes, and you could actually bound just the. You're saying that we could bound just the Taylor expansion coefficient instead of the difference between the Taylor expansion coefficients.
Exactly. Yeah.
That's true.
Okay, so that difference was taken just because you wanted to make connection to knot polynomial.
Yes,
is that right?
Correct.
Okay. Thank you.
Okay, so let's go through phi cube theory. So I wanted to go slow here because I was throwing a lot of information at you, so I want to write out. So you could work with phi cube theory, so massive phi cube theory, or you could work with, say, phi square psi, where phi is a massless scalar and psi is a massive scalar. So this is what I'm going to work with. So let's write down the tree-level amplitude for this phi square psi theory for phi to phi scattering. So this is going to be equal to m square minus s1. So here s1, s2, s3 are the Mandelstam variables. And because the external particles are massless, I'm going to simply have s1 plus s2 plus s3 equal to 0. If you wanted to work with pure phi cube, then you just have to shift. So if you wanted to work with s plus t plus u equals to 4, then you would just write s equals to s1 plus 4 by 3, t to be equal to s2 plus 4 by 3, and u to be s3 plus 4 by 3. And so that s1 plus s2 plus s3 is still equal to 0. So this is the amplitude that you know. This is the simplest thing that you could possibly think of in quantum field theory. And of course, the point is that we are not going to work with the Mandelstam variables, but we are going to work with some new variables, because it turns out that for a manifestly crossing symmetric dispersion relation, the Mandelstam variables are very uncomfortable, so they are not very useful. Sandeep, you're sleepy, so
sorry.
So it'll become exciting in a bit, don't worry. So S subscript k is, so the way that we're going to write down is we're going to parameterize S subscript k like so. And these zk's are the cube roots of unity. So zk's are exponential of 2 pi I k minus 1 by 3. Okay, so I've just introduced a new set of variables. So instead of S1 and S2, I'm going to work with A and Z. So originally we had two functions, so this was S1 and S2. So I'm going to now do a change of variables, and I'm going to work with A and Z. So if you actually do this calculation, it's quite easy to do, but then you could just substitute. You will see that A is simply S1, S2, S3 divided by S1, S2 plus S1, S3 plus S2, S3. So these set of variables were first introduced by Oberson and Khoury in a very less cited paper in 1972. And I guess for various reasons, it wasn't followed up on at that point of time, but these variables are going to be quite useful for us. So this M, this tree level amplitude, you can actually verify that it takes on a very simple form. So what will happen is that instead of Z, because of this full crossing symmetry, only Z cubed is going to appear. So you don't get just single powers of Z, it will only be powers of Z cubed. So I will introduce a new variable, Z tilde, which is just Z cubed. And this is something that you can verify. This is a straightforward calculation to verify that this amplitude here for phi square psi is basically a constant, and this constant will actually play a role in the dispersion relation. So this will be like a phi4 contact term that I need to add in the dispersion relation. So you can do this calculation and verify that this phi cube theory is nothing but this, where beta hat, so let me just write out. So beta hat is given in terms of the mass and this A parameter that I introduced. And psi, now this is the important thing. So far, I did not give you a precise relation that relates psi to anything physical, but this is the relation between psi and the physical parameters.
What is M?
M is the mass of the, so I was thinking about phi to be a massless scalar and M to be the mass of the psi exchange particle. Okay.
I have a question.
Yeah.
So this, when you expand this Chebyshev polynomial or whatever, generating function null, you would get more than three terms, right? I mean, so I don't see how it will lead to a sort of the expression that you had before. This expression, yeah. No, not this. The 1 minus 1 by 1 minus t plus 1 by 1 minus S1, etc., etc.
Where, sorry, this one?
Yeah, this one. 1 by m square minus S1 plus 1 by m square minus S2. This is just three terms.
Yes, but S1 plus S2 plus S3 is 0.
Sorry?
Subject to the constraint that S1 plus S2 plus S3 is 0,
Yeah, true.
Yes. Yes.
But when you expand this m z tilde a,
Yes.
in
I'm
terms
not
of
expanding. This is an exact statement. So there is no expansion here. This is not an approximation. This is an exact statement. I do a change of variables. I go from here to here.
yeah. I mean, I understand that, but what I'm just concerned about is whether when you rewrite the rewrite the generating functional in terms of the variables of the S1, S2, S3, whether that will lead to just 3 terms, because in general, it's a generating functional which leads to a arbitrary polynomial when expanded in, say, Z tilde.
Sorry, I'm not sure I follow the question. So from this guy is simply a change of variables from here using these guys. Just plug them in here, you will get this.
Okay, maybe just continue. Just
Yeah. Yeah, I'm not sure I followed the question. So, but yeah.
There is a confusion. I think maybe some notation. You are using m squared. So
yes.
S looks like the usual Mandelstam variable, right? Not no shift, but you are still using S1 plus S2 plus S3 equal to 0.
Yeah, so I was doing it in a slightly different theory, not in the phi cube theory. I was doing it in the phi square psi theory, where phi is
psi has mass m. I see.
Yeah.
I see. Phi is massless and psi has mass m. That's your theory.
This is m equal to 0 and this is m.
Okay.
Yeah, this is just for simplicity. You can do it for phi cube theory and do this shift.
Okay. Yeah. Thank you.
Sorry, just a trivial clarification on India. The full amplitude will be multiplied by coupling constant square, right?
Yeah. So that I've sort of factored out. So
that's fine. Thank you.
So whatever you did, can you also do it with phi times psi squared when psi is massive? Like the vertex has two fields which are massive instead of one.
Yeah, you could do it for that. I mean, you'll require some. So long as you have full 3-channel crossing symmetry, you could do it for massive theories as well. I mean, this is just so that I didn't have to do this extra shifts, but indeed it will be true for any massive theory. Okay. Now,
Aninda, this particular denominator is a coincidence. So right now, at least.
Coincidence in the sense that this is exactly going to be the same that will appear in the crossing symmetric dispersion relation. So you could think of the crossing symmetric dispersion relation as an integration over phi cube theories.
But also this guy is the denominator of the generating function of this Chebyshev and so on, right?
Yes, exactly.
Okay.
So are you saying that this term would give rise to an expansion in many masses or something?
Not many masses. It is going to give rise to an expansion in Z tilde n, whose coefficients are going to be Chebyshev polynomials in psi. Yeah, so I will write this out. So let me. So I will write down one more equation and then perhaps.
Okay.
So this is going to be equal to 3 by m square plus beta hat by m square, and this guy is summation n going from 0 to infinity. These Chebyshev polynomials of the second kind, z tilde to the n plus 1.
Yeah, so that was my point. You initially had 3 terms. Now you are having an infinite number of terms. How is?
Yeah. So okay, no, I understand your question now. So you're not going to get So depending on which Taylor expansion coefficient you're considering, you'll get a specific knot polynomial. So remember, we will get all the a to 2n plus 1 appearing depending on which combination you're taking. It's not a single knot polynomial that appears. So, okay. So let me just write down one more thing and then it'll become clear. So using this, it is straightforward to see that now this is going to make that equation most precise, what I wrote in the first slide. So you're just basically taking the Taylor expansion coefficient of M and forming this combination. So these are basically various combinations. So let's give this a name. We'll call this rho n. And rho n is just using the above identity. It's just the difference of two Chebyshев polynomials, and hence this is just the Alexander polynomial. So this is equal to a. Sorry, not psi, but p.
So is there something natural about the way you have chosen the variable xi? I mean, if we didn't want to make connection to not polynomial, would it still be natural to choose xi this way?
Oh, you mean this choice?
No, no. The xi and the a over m square ratio, right? That.
Oh, this one. No, this just appears naturally. So the way that this is just from the change of variables. If you look at, if you rewrite it, you will see that this is the combination that appears. I have not chosen psi. It is just how it comes out.
But xi has an independent definition.
So I have just identified this combination here to be 2 psi. So if I just plug these guys inside here, yeah, I will get this form with the choice that psi is this.
Okay.
With the identification, I shouldn't say with the choice. With the identification that psi is this. Is that clear? Yeah, because it's an important bit actually. Yeah.
I'm a bit confused with your variables. So your z tilde was z cube.
Yes.
But what was z to begin with? Sorry.
Oh, okay. So I parameterize the Mandelstam variables this way.
Right.
Okay. So the reason why I parameterize it this way is because when I do a fully crossing symmetric dispersion relation, I want to hold a crossing symmetric combination fixed. So the way that one way to do it is to hold S1, S2, S3 divided by this. So this is the cubic Mandelstam invariant divided by the quadratic Mandelstam invariant, the fully crossing symmetric object. We want to hold this fixed when we write down the dispersion relation. So that's the logic. So usually when we write down dispersion relation, we hold T fixed. But because we hold T fixed, we lose manifest crossing symmetry. But if we want to write down a dispersion relation which is manifestly crossing symmetric, you want to hold something like this fixed.
I see. And then the claim is that as long as your 2 to 2 amplitude is crossing symmetric,
yeah,
then you can change variables to get it into this form where you have some generating function.
Yes.
Okay. Thanks.
So is the understanding that for this particular case, you get this sort of expansion, and all the other rest of the cases for general cases where you don't have a single particle being exchanged but a multitude of particles being exchanged, you have a similar sort of expansion. Is that
yes.
The idea?
So that is what I'm going to come to next. So this is so you're asking what happens when it's just not phi cube theory, but suppose, for example, string theory, 3-level string theory. What will be the form?
Not even 3-level string theory. Some sort of interacting field theory.
Sure. I mean, as an example. So let's say
as an example, yeah.
As an example, suppose we want to do it for 3-level string theory.
Okay.
I will show you the answer. Yeah.
Okay.
Okay. Aninda, so the argument that you gave explained why A is special. Yes. Now, why introduce Z that way, that particular way? I mean, you have taken inside this particular combination, Z minus ZK cube over Z cube minus 1. Is there something special about the way?
Yes. So you want to actually, so the way that it works, although I presented it sort of in a reverse way. So what you want to do is you want to parameterize something such that this condition holds, and such that you can hold this fixed.
I see.
Okay. So that introduces this way of writing Z. So now there are more complicated parameterizations that people have used. So SM Roy and Mahooks and Wonders, they use a more complicated parameterization. But for simplicity, I'm going to use this one.
Okay. Okay. Thank you.
I have another question. Is there sort of a generic proof that you can't cross the Alexander polynomial boundaries? Or
yes. I will show you. Yeah. One can derive it. I will show you the derivation here. So the other thing, I just wanted to spend a bit of time because this is kind of a big deal here. So psi. So what can we say about psi? Because that is going to be, after all, related to the parameters. So a couple of interesting observations immediately you can make. First of all is that, so first look that A is dimension full, okay? Because there are 3 powers of Mandelstam on top and 2 powers in the denominator. So it will be a dimension full quantity. So you can think of it having a dimension of mass square. So A by m square is dimensionless, A by m square is dimensionless. And you can ask what happens when A by m square goes to 0. So obviously when A by m square goes to 0, psi goes to 1. So when psi goes to 1, this is the same thing. So remember that psi was this guy. So this actually means that if psi goes to 1, the knot parameter goes to 1. And if the knot parameter goes to 1, so let's go back to the maths background. So if the knot parameter goes to 1, all your Alexander polynomials become 1. So the Alexander polynomials become the same value as what an unknot would take. Okay, so that is something that is important to remember. You could actually ask when is psi equal to -1? So when psi is equal to -1, let's write it in blue. So psi becomes -1 when A by m square is equal to -1/3 or 2/3. And so if psi is equal to -1, this actually implies t is equal to -1. And why is that important? It's because when t is equal to -1, I get a knot invariant which is related to the crossing number.
I have a related question. When you have xi equals 1, isn't it essentially equivalent to the 5/4 theory?
No,
the 5/4 theory, yeah.
The 5/4 theory is just this. Yeah. So okay, that's kind of an important point when psi is equal to 1. So when psi is equal to 1, so let's see. I should have left bigger gaps, but doesn't matter. So when psi is equal to 1, this actually becomes a very interesting object. This becomes 1 minus z tilde square. Okay. Z tilde over 1 minus z tilde square. Now, why is this important? Why is this interesting? It is interesting because if you do a Taylor expansion of this guy, you will see that this actually looks like z tilde plus z2 times z tilde square plus 3 times z tilde cubed plus etc. plus n times z tilde to the n and so on. So this, if you remember, I told you I made a big deal about the Bieber-Bach conjecture somewhere. Where is it? Here. So here. So I said that the Bieber-Bach conjecture says that it should be less than n should be less than n. So when psi is equal to 1, we get a function which actually has a name. It's an extremal function. It is a function that maximizes the Taylor expansion bounds. This is actually called what is called a Kobe function. And that is important for another reason. The other reason is that if you have 2-to-2 dilaton scattering with the graviton exchange, then that amplitude is basically just nothing but A times z tilde over z tilde minus 1 square. So this extremal function is actually very important because of these reasons.
Okay.
Yeah.
So Aninda, just one kind of question. So far, I mean, the connection with the knot seems a bit, kind of.
Yeah. So.
Yeah. Sorry.
You mean that? Yeah. It's not a natural connection. Yeah.
Not a natural connection. Yeah. So far.
Yeah. That is a fair criticism. So it'll, but I will extend it. I will tell you I mean, right now my focus is to get the knot polynomials, and I want to say that I can derive the boundaries of certain combinations of these Taylor expansion coefficients in terms of these knots. And then I will try to reinterpret the dispersion relation in terms of an average over the knot parameter. And that is where I think the interesting thing is going to come, because we don't talk about such things in knot theory.
Would things apart from the torus knots also come, or rather 2 comma q also come?
Yeah, so you could, but the point is that you could form various combinations of these Taylor expansion coefficients.
Okay.
And so what will happen is that you could come up with 3 comma p kind of knots as well. And that will relate, that will depend on other combinations of the Taylor expansion coefficients. So basically, you can get any knot polynomial by taking various combinations of these Taylor expansion coefficients. So I could get the Jones polynomials for the torus knots using this.
Okay.
The only difference, yeah. The only difference, yeah.
Go ahead.
Yeah. So the difference is that for the Jones polynomial, I will require 3n Taylor expansion coefficients rather than the 2 for any n that I have for the Alexander polynomials.
Okay.
Yeah. So my question is, this particular row that you have seems to be kind of generated to give rise to the
yes, that's what Abhijit was. Yeah, that's what Abhijit was asking as well. Yes.
Yeah. So it's not sort of natural. I mean, you could have any sort of function instead of row.
Yeah. Right. So natural, of course, it depends on what you mean by natural. So here I'm saying that the Alexander knot polynomials are related to the derivative of the simplest amplitude that we could think of. So, so in that sense, it's a nice connection. Now, natural, I guess you want to say that something is natural if I write the amplitude itself directly in terms of the knot polynomials.
Or rather,
the phi cube interaction has anything to do with the crossing number 3, then it would have been even more interesting, right?
Yeah. So unfortunately, it is not just the crossing number 3 that we get. We get 2n plus 1. So the Taylor expansion coefficient of the phi cube theory itself has all crossing numbers starting from 3 to 2n plus 1, when n goes to infinity.
Yeah, and another related point is, like, what is the exact interpretation? I mean, you had 3 terms to start with, and then you have an expansion in terms of the Alexander polynomials, which goes to infinity.
Yes.
So
but you see, I mean, here I could have expanded in terms of, so I could have written this as sum over WPQs S1, S2, S3 to the power Q times S1, S2 plus S1, S3 plus S2, S3 to the power P. So
yeah, I agree.
This also has an infinite number of terms.
True, I agree. But I mean, apart from the display that it is amenable to be written in this form, is there any advantage to writing it in this form?
Well, yes. So I can identify what the boundary curve is, for example. So that's what I will show you. So what one application as to where these Alexander polynomials enter.
Yeah, but the boundary curve would vary from choice of row from different functions of row, right?
Yeah, no, but that is always going to happen. So, I mean, the boundary curve in theory space, you can always rotate in theory space and get a different coordinate system. So that is expected. So that is not so I'm saying that this is the boundary curve if I orient myself in a certain way.
What is the advantage? That's what I'm asking. What is the exact advantage of doing it?
Why don't we continue, and then you will see what the advantage is.
So one more question. Can we just extend this analysis to the case when there are massless particles present? Because you talked about dilaton scattering with graviton.
Yes.
Exchange.
So you could talk in terms of massless external states with massive exchanges. Taking into account massless exchanges is a bit tricky, but you can do it. So let me just come to the massless exchange at the end. But I'm going to actually show you a formula for the dilaton scattering amplitude in string theory in a bit.
Okay, thank you.
Okay. Yeah. Okay. So the story so far is that I can take a particular combination of the derivatives of the amplitude and I can get the Alexander polynomial. And now, so what I do with it? So this is where the crossing symmetric dispersion relation is going to play. So now I cannot derive the crossing symmetric dispersion relation for you because that will take another 3 hours. But I can tell you the background of the crossing symmetric dispersion relation. So the crossing symmetric dispersion relation is an attempt to write a representation of the amplitude in a manifestly crossing symmetric manner. Now this is completely counterintuitive because if you open Green-Schwarz-Wheaton chapter 1, you are going to learn that you either expand in terms of the S-channel pole or in terms of the T-channel pole, but you never actually talk in terms of both poles at the same time. So, but here the crossing symmetric dispersion relation gives you an expansion in terms of the poles in all 3 channels at the same time. Now, this is completely counterintuitive in many senses because first of all, and rightly so, if you just naively write down the residues divided by these poles and just add them up, that is the wrong answer. So, because you will find that the sum does not converge, it is not a good representation of the amplitude anywhere. So obviously, let me just continue, and then I will.
No, it's a simple question. I mean, yeah. It's a question regarding string theory, which I need to know. Which is that if you have a sphere, then it can be written either in terms of a T-channel expansion or a S-channel expansion, right?
So I'm going to give you an explicit answer to that question. So that is where the crossing symmetric dispersion relation is going to be handy. So you're
so the statement that you just made, that in string theory you in Schwarz-Wheaton it is said that the T-channel and the S-channel can't be related to each other. That's what I'm questioning.
No. The statement is not that the S-channel and the T-channel cannot be related to each other. The statement is that when we actually write down, and this is motivated by the dispersion relation, the fixed T dispersion relation, we either expand in terms of the S-channel pole, depending on whether there is the U channel cut. So it will be either the sum of the S channel pole by the plus the U channel part, or you expand in terms of so you basically expand in terms of the poles in 2 channels. So that is the outcome.
But crossing symmetry means that the 2 can be related. That's what crossing symmetry means, right?
No, crossing symmetry means that this can be crossing symmetry is an extra condition which relates this S plus U to T plus U. Yeah.
Okay.
Yeah. So let me just, because I will give you an explicit example which will clarify your doubt. So after I show you the explicit example, maybe you can ask your question again. Okay?
Yeah.
Yeah. So this is motivated. I'm doing very badly with time. Abhijit, how much time can I take?
Yeah, I think it's okay. You can go. I mean, how much time do you think you need?
So I had the crossing symmetric dispersion relation. I wanted to work out the bounds, but now I realize that I should have written it out. And then I have the story about the Q deformed harmonic oscillator. So I guess at least 20 minutes.
Okay. So let me just request the audience that maybe we should let Aninda make considerable progress with his talk. And only if it is urgent, then we should ask the questions now. Otherwise, let's reserve our questions towards the end. Okay,
Yeah.
Aninda. Sure, please go ahead.
Yeah, I mean, yeah, so clarifying questions is, I don't want to not let you ask questions. So just ask me questions, but maybe then I will have to sacrifice some of the material towards the end. Yeah. So the crossing symmetric dispersion relation was first introduced by Robertson and Khoury in 1972. And then we resurrected it in a paper with Ahmadullah in 2020, primarily because we wanted to understand Polyakov bootstrap. So this Polyakov bootstrap was solved, the derivation was given in this paper. So the statement is that you have a fully crossing symmetric amplitude. And as I said, I'm going to focus on where there are no massless exchanges for now. It has a representation which is fully crossing symmetric in the following sense. So I should have written out one more expansion. So sorry about that. So let me just, so Z tilde, how is it related to the original parameters? So I should have written out the answers. So S1, S2, S3, which I can call Y, is actually up to some signs. It's 27a cubed times Z tilde over Z tilde minus 1 square. And X, which is the quadratic invariant combination, is 27a square times the same quantity. So yeah. So the crossing symmetric dispersion relation takes on this form, which has some superficial similarity with the fixed T dispersion relation, but there are some crucial differences. So this is the absorptive part of the amplitude. Now, the absorptive part of the amplitude, similar to what you do in the fixed T dispersion relation, you integrate over S1, S1 prime or S, whatever you want to call it. So, and the first argument in the absorptive part is the integrated variable. In the fixed T dispersion relation, this is what you would have replaced this by T, but in the crossing symmetric dispersion relation, it is replaced by something more complicated. It is in terms of S1 prime, which is the variable that is getting integrated over, times this object. Okay, so this is where A enters. So S1 prime is getting integrated over. A is this parameter that I introduced, which is this cubic invariant by crossing by the quadratic invariant. So this object here is manifestly crossing symmetric because A is made of crossing symmetric objects. Then times some combination which depends on A square and S1 prime. So again, this is also manifestly crossing symmetric, and times this kernel. And this kernel is also manifestly crossing symmetric because it depends only on Z tilde. And Z tilde can be recast in terms of just X and Y. So is this clear why this is a manifestly crossing symmetric object?
In the in the usual dispersion relation, one also does some subtraction. So there's some division by. So,
very good, very good. So here I have assumed in writing down this dispersion relation, one also assumes, not assumes, one can actually demonstrate this. We use two subtractions. So this is the usual thing that you have in the massive case, which follows from the facade bound.
Okay, okay.
What is the original expression from which you are getting this by making a change of variables?
So we are working directly in the Z variable. So we are writing down a dispersion relation in the Z variable holding A fixed.
True, but I mean, Z and A you have got by redefining the original variables.
Yes.
So shouldn't you start out with the original expression in terms of the original variables and
no,
then?
There is no original expression. So this is a new dispersion relation. So this cannot be derived from the fixed T dispersion relation. So there is no derivation from the fixed T dispersion relation. This is a new dispersion relation which is in the Z variable.
So what is the guarantee that this is correct? How are you ensuring that this is correct?
Because we are making the same assumption. So whenever you write down a dispersion relation, you're using properties of complex analysis. So once you know that there are no poles in a certain region, you're allowed to actually deform the contour and wrap the contour around the curve that has branch cuts.
Yeah,
so
but that can be done in many ways.
No. So in that particular case, so I don't have time to go into this. So let me just demonstrate that it works. So maybe that might actually satisfy you. Yeah. So because addressing all these questions will take a lot of time. Unfortunately, I can't give you a very simple answer. So the one thing is that this kernel, which is going to play a major role, you get similar results for position space dispersion relations as well in conformal field theories. So this is something that I have been looking at with IISc recently, and then in fact, whatever I'm saying, this particular kernel, the property of this particular kernel is exactly what appears for the dispersion relation in defect CFTs, which was recently written down by Liendo and collaborators. So this is basically very similar to the phi cube theory, so except that we have dressed it with various factors. So there is this dressing factor here. And what we are doing essentially is we are integrating over psi. So imagine that we hold A fixed. So integrating over S1 prime is the same thing as integrating over psi. So that's what we are doing. So that's the dispersion relation. So let me give you an example. So this is a 2-to-2 dilettone scattering in type 2 string theory. So this is the representation using the dispersion relation, and why this representation is correct, you can just do a low energy expansion of the known answer, which has been studied for a long while, for example, in papers by Michael Green and collaborators, and you can compare with that expression. So let me just go through it quickly. So there is this massless pole plus a constant, which is the famous r to the 4 term, 2 zeta 3, plus something which looks like you have this kernel, except that you're summing over. You're doing something very interesting. You're actually summing over this k parameter. So k is the level number, and each psi is labeled by k. So you're basically integrating over size, exactly what the dispersion relation says. And what is this psi k? So psi k is precisely this object here. So k is a level number. And so in terms of this q parameter, the q parameter which enters the knot polynomial, you can think of this parameter as being quantized. So for a fixed a, you have quantized values for q. These mu k's can be worked out explicitly. They are given in terms of Pochhammers. So I was trying to explain that it is not simply that we are adding the 3 channels. It is not as simple as that, because we know that that does not work. So you must have paid a penalty somewhere. Where is it that you paid a penalty? This is where you paid a penalty. So let me just go through this formula, parse it for you. So what is this lambda k? So lambda k is some square root object like this. So in particular, it has poles when a is equal to k. Or in this particular, lambda k square has poles when a is equal to k. And these are Pochhammers. So Pochhammers are basically polynomials because these are integers. So anytime you have something like this, it is a polynomial. It is symmetric under lambda k going to minus lambda k. So only lambda k square is going to appear in the expression. So if lambda k square appears in the expression, you will see poles corresponding to a equal to k. Okay. So for example, I've listed out specific examples. Mu1 is this. So mu1 does not have a pole. So the level 1 does not have a pole. That's an interesting thing. From level 2 onwards, you get multiple poles. So level 2 has a simple pole at a equal to 2. Level 3 has a double pole at a equal to 3, and so on. So that is the structure of these mu k's which weight this kernel. Okay. Now, what is going on? So this is what is going on. Now, I should write it in multiple places. A is a ratio of these two. So if you have very high powers of A, you will see very high powers of this in the denominator. Now, if you have very high powers of this in the denominator, it is not of this form here, where you expect only positive powers of this quadratic invariant and cubic invariant. So the penalty that you have paid is that for a fixed level, you've lost locality. So for a fixed level number, you don't have locality. You recover locality only when you sum over all the levels. And that you can play with, and manifestly, I've written out the expression. It is there in the appendix of my paper. You can play, and actually you can manifestly convince yourself that locality is recovered once you actually sum over the level numbers. So this is what enables us to actually have a manifestly crossing symmetric expression, but the penalty that we pay is that we sacrifice locality. So obviously there is a way to rewrite the locality constraints, and when you rewrite the locality constraints, you can simply rewrite it in terms of the knot polynomials. You can, so these are these mu k's. So the locality constraints are simply that when you sum over mu k's weighted by the knot polynomial, you should only get a polynomial of degree 3n in A. That is the statement of locality. And I would like to say that for a fixed level, this actually, you can think of the left-hand side as a measure of knottiness, because if, okay, I want to introduce this term knottiness. I don't know if it has been introduced, but it's a fun term to introduce. But if qk is equal to, is different from 1, then obviously you'll get some knot polynomial that is different from 1. And it will tell you how much knottiness is there in the expression. Now, there is something else also that you can do, and that is you can split the sum into 2 parts. One of them is you can split it up to k0. K0 is some large number, and then the second part is k0 to infinity. So this k0 to infinity actually can be done explicitly, this part, and it takes on a universal form. This sum from k0 to infinity just takes on, it's just proportional to this Kobe function. It's an extremal. So this k0 to infinity, this large K tail of string theory saturates the Bieber-Bach conjecture. Okay.
Can I ask a question?
Yes, Shamdatta, yes.
So this thing you're doing, it's generic, right? It's applicable for all possible theories, right? Writing down the crossing symmetric expression and so on.
Yeah, provided it falls off fast enough at infinity.
Yeah, so it should be applicable also for the previous case. I mean, for the phi cube case that you had treated before.
Yeah.
So, but for the phi cube case, we know what is the expression for that particular m that you had.
Yes.
Isn't that right?
Yes, but
so,
the phi cube case
can you relate your crossing symmetric relation
to
the original expression?
Yes, yes, of course. I mean, that is just a delta function support at a certain value of k, and it's given in terms of just this quantity. Yeah, phi cube theory is just a trivial object.
Okay. I mean, I suppose you have checked it, right? I'm just asking.
Yeah. I mean, phi cube theory, you don't have to, you don't encounter this problem with non-locality, because it's simply you get one level. You just get that guy. Yeah. The problem with locality comes when you try to add level 2 or level 3 onwards.
And those come in because of string theories or something?
Yes. Yeah. So you can have the statement is that if you don't introduce any spins, so only have scalars, then this dispersion relation is not going to give you anything new apart from phi cube theory. So the interesting constraints which come from these kind of locality constraints, or what people call the null constraints in the other dispersion relation, these arise because of the other levels.
But is there an independent way of verifying whether your crossing symmetric relation is the right one?
Yes. The independent way is that there are analogous constraints to these locality constraints, which come from the fixed T dispersion relation. So in the fixed T dispersion relation, you get additional constraints on imposing crossing symmetry as an extra condition. So you get an extra set of constraints. You can actually show that these locality constraints are the same in that case. So linear combination.
I have a question.
Yeah, Ashok, yeah.
I mean, you talked about string theory, but string theory, of course, has massless gravitons. I mean, I somehow missed probably where those
so
were.
I have actually subtracted. I've written this out separately. So I'm focusing on. I'm trying to describe the level 1 onwards using the dispersion relation.
I see. Okay.
Okay.
Okay. Yeah. And this is tree level only?
The example that I've shown here, these expressions are for tree level only. Yeah.
Okay. And in the dispersion relation, how exactly do you put that in, that you are working with a tree amplitude?
Oh, in the dispersion relation, I don't. What I did was I just used the absorptive part of the known string tree level amplitude. So in terms of the gamma functions, I look at the poles. So the poles correspond to the absorptive part will correspond to delta functions, and I just do this integration.
So this involves the gravitons in the loop?
No. So this is at tree level, right? So what I've done is I've subtracted out the massless pole, so that I've written that out separately, and I've expressed the rest in terms of the absorptive part.
I see. But rest means just a tree level amplitude.
Just the tree level amplitude. So in this particular example, where I've worked out this mu k, etc., it's just a tree level amplitude. Yes.
Okay. Okay.
So you have derived it from the sphere amplitude, right?
Yeah.
Okay.
I mean the gamma function representation of the sphere amplitude, not starting with the sphere amplitude, not in the
yeah, of course.
Okay. Any other questions? So then let me just quickly derive, because it's a 3-line derivation so far as the bounds are concerned. So I will start with this definition of rho n that I introduced here. Use the crossing symmetric dispersion relation. So what I'll get is rho n, and so I'll put a modulus sign is equal to the combination of these derivatives evaluated z tilde equal to 0. So this is going to be equal to some integral, and I will convert the, so here I could convert this integral into an integral over psi. So I will call that some integral over some measure factor, psi min to psi max, and times, so this will become the absolute value, and this will become the Alexander polynomial. And now this is where we have to restrict the range of A, because what I want to do is I want to apply the triangle inequality. So in order to apply the triangle inequality, I need to make sure that this d mu psi is a positive measure factor, and that gives me a range of A where it's a positive measure factor. And the triangle inequality simply gives me this. And the next line is trivial. It just becomes a supremum of the knot polynomial in this range. And finally, there is a global bound that you can derive, which is basically the knowing what the maximum or the value that the Alexander polynomial can take inside the appropriate range, and the maximum value is basically just given by the knot determinant or the crossing number. So this is equal to just 2n plus 1.
Sorry, Aninda, what is the physical origin of these bounds? Unitarity bounds?
No, so unitarity plays a role here. So I pulled out this measure factor, right? So in order to pull out this measure factor, this measure factor, roughly speaking, is some ds1 over s1 prime prime, and then the absorptive part. Okay, so that's roughly speaking the measure factor times something. So this is what I'm writing as d mu. Okay, so and then I want this to be a positive measure factor, which means that I have to be in a range where this absorptive part is positive. This absorptive part is positive. So how would we? This absorptive part is in turn given by the partial wave amplitudes times the Legendre polynomials, and so what you have to, so this one is going to be bigger than 0, and you have to determine where this Legendre polynomials are bigger than 0. Okay, and that is what gives me a range of A where this is true, and that is why you see that I have plotted over a restricted range of A.
Okay, so this is unitarity, right?
This is part of unitarity. The full statement of unitarity also involves this nonlinear bounds of.
Yeah. No, I mean, I don't mean the full consequence of unitarity, but it is coming from unitarity. Okay.
Yeah, so when you are doing this, when you're extracting out the measure factor, you have to take the maximum value of the A, right? That's what you mean by taking the supremum. And the measure factor also has a certain value.
Yeah, so the way that it is done, so the way that I've normalized things, the measure factor integrates to 1. That is how the normalization works.
Okay.
Yeah, so this integral over d mu is actually 1. So I have given you another example. So this was the first derivative. So rho n was equal to 1. Rho 2 also has a similar thing. And then as you can see, the bootstrap and this purple thing appear to behave very well, very close to each other. So the same story that I told you in the beginning also happens for the higher ends. And this black line is what comes from the Bieber-Bach conjecture. And the Bieber-Bach statement is simply that. So this 2n plus 1 is basically what comes from these geometric function theory considerations.
Okay. These blue lines, have they appeared before?
No. You cannot. You can derive these numerically using the fixed dispersion relation if you do some change of variables, but you cannot derive them analytically. So the way that you would do it in the fixed dispersion relation is you would first do the two-sided bounds on the Wilson coefficients, and then rewrite this rho 1 and rho 2 in terms of those two-sided bounds.
Okay.
I have a related question. The way you have defined rho, it's kind of automatic that you would get something like the Alexander polynomials on the right hand.
Completely,
right?
yeah.
Okay.
Yes, that is correct.
Yeah, but okay, fine.
Aninda, I mean, is it correct to say that if you didn't insist on not polynomial, you could have gotten more bounds?
No, that's a good question. So I think because of the fact that the not polynomials have the same information as the Chebyshev polynomials, because I am taking the difference of two quantities, right? And if I just work with the
what
Chebyshev,
if you didn't take the difference?
Yeah. So in case yeah, so I could have worked with the Chebyshev polynomials directly. I would have gotten analogous bounds, but these analogous bounds would be related to whatever bounds I'm getting here. So I think that's the correct state. So why I'm saying that?
Ashok is trying to say there's nothing special about the Alexander polynomials, I suppose, right?
Yes, I agree with that. Yes. I'm just saying that in this way of writing things, I can interpret the boundary as Alexander polynomial.
But couldn't you have gotten that bound on the individual objects rather than differences? Because here you have to always take differences, right?
No, so I actually should have told you this, that I could have done it in a manner that I could have removed this modulus sign. I could have done it in a manner where I'm not bounding the absolute value. So when I derive the bounds, when I'm not bounding the absolute values, the content that it has, those bounds have, is the same as what I would have gotten using the Chebyshev polynomials.
I see. Okay.
Yeah, because in the what we do is we always derive projective bounds.
Okay.
Yeah, so the projective bounds have the same content in both cases.
Okay. Yeah. Thank you.
Okay. So yeah, so as all of you have correctly surmised, the way that I've introduced these not polynomials might seem like I'm doing something artificial. I'm taking some special combinations, but that is not the objection that you should have had. The objection that you should have had is that here I have the Alexander polynomial, but actually I'm averaging over the knot parameter. So it is not just a single knot polynomial that I'm getting in the representation of rho n, or when I'm writing the expression for rho n. I'm actually getting an average. I'm getting something that I'm a sum of knot polynomials, so to speak. So the correct objection should have been that what is the meaning of this averaging over knot polynomials? So what does averaging of
wait? Why are you averaging over knot polynomials? Because mu doesn't contain
I have
n.
a single knot polynomial here, and I'm integrating over psi, and psi t and psi are related. So I'm sort of taking an average. So this you can think of it as a probabilistic measure factor, because it has the properties of a probability, and so you are doing an average over the knot parameter.
Yeah, but the average is not over n.
It is an average over t.
It's an average over t, but t is just a parameter which you can always integrate over. So
no,
I don't see any problem with that.
Yeah, so the point is that what does it physically mean? Because if I just added up the knot polynomials, that wouldn't be a knot polynomial. The sum of knot polynomials is not a knot polynomial.
Knot polynomials as such are discerned by the n's.
No. Polynomial parameter is t.
Yeah, but I mean, I suppose you can always integrate. It's just a parameter. There's no harm in integrating over it.
Yeah, but what does it physically mean? So you can integrate, but what does it physically mean? So the question that I want to address is what is the physical interpretation of this integration? Okay. So let me tell you my understanding of it, or whatever we've come up with so far. And for that, I require to introduce something called a Q-deformed harmonic oscillator. So in the next 5 minutes, I will complete in 5 minutes. Sorry for going so much over time. So what I'm going to talk about is a Q-deformed harmonic oscillator. So this was introduced in 1989 by Biedenharn and McFarlane. So some of you have heard of Biedenharn. McFarlane actually was a physicist in Cambridge who taught me Lie algebras and particle physics in my part 3 course. So we want to ask if you can give some kind of a physical picture as to why we are getting bounds, and what is there some other way of coming to this generating function of the knot polynomials. So what is this Q deformed harmonic oscillator? So like you have in the ordinary harmonic oscillator, if Q was 1, then you would have just gotten the usual harmonic oscillator, but Q is a deformation parameter. So you talk in terms of 3 generators, A, dagger, and N, and you introduce this algebra, which is called a Q deformed harmonic oscillator algebra. So so you have this expression, and then you have a commutation relation between N and A. This Q can be thought of either as a real number or a complex number. And in my case, this restriction that I talked about, 2 psi or psi, modulus of psi being less than 1, this is also related to the fact that I want a positive measure factor. This actually converts Q here to be a phase. So Q can be either a real number or a phase. Now, when Q is a phase, you can take the Hermitian conjugate of this expression and you get another expression like this. And then you can subtract off 1 and 2, and what you will get is an expression for A dagger A in terms of Q. So this is what is the definition of a Q number. So if Q was 1, you would literally get N here, but Q is away from 1, you get what mathematicians call a Q number. It's a generalization of ordinary numbers. And a remarkable fact is that these Q numbers are related to the Chebyshev polynomials. And this is going to play a role in the rest of my story. So you can ask, how do I write down the states in the Hilbert space? So it's in the usual way. So you define a vacuum, you define an eigenvalue or eigenstate for N. So in A dagger acting on N will look very similar to what you get in the usual harmonic oscillator story, except instead of the N plus 1, you get the N plus 1 Q deformation of N plus 1, which is this guy. Similarly for A, and so on. Now, it's a very simple exercise that if you start off with a Hamiltonian that is given by this, because of the fact that N acting on N is equal to little n times N, you can consider the thermal expectation value of A dagger A. So the thermal expectation value of A dagger A is simply the Q numbers weighted by e to the power minus beta n. Why is it e to the power minus beta n? Because n acting on capital N is just little n times the state. That's why it's just e to the power minus beta n. And then you work it out. You can do the sum explicitly. You will get this expression here. This expression here looks very similar to whatever we have studied so far, whatever we have been discussing so far. It's 1 minus z tilde over this quantity up to this factor. If you identify z tilde to be e to the power minus beta omega, so that actually the 0 temperature limit is the center of the z tilde plane, and infinite temperature limit is approaching 1. So this is like the low energy expansion, and this is like the high energy expansion. So in this map, the low temperature, the 0 temperature is like the low energy expansion, and the infinite temperature is like the high energy expansion. And then you can write down that the amplitude is simply the partition function times this average of the 2-point function, or the thermal 2-point function. Okay, so this is a map from the dispersion relation to this Q deformed harmonic oscillator. Now, this is some averaging, but averaging of what kind? You cannot have averaging of any kind that you want. It's a very specific kind of averaging. And the kind of averaging that you want are just the generalization of the locality constraints that I exhibited. So these are just a statement in terms of these Q numbers integrated over this probabilistic measure factor, the fact that it should be a polynomial. So you can derive some immediate consequences. So for example, you got two-sided bounds for these Wilson coefficients. So in this harmonic oscillator language, what is the interpretation of these two-sided bounds? The reason why you get two-sided bounds is simply because in the Hilbert space, you have finite norm states. And that is enough to give you these two-sided bounds. And you can get some other physical pictures as well. For example, near this parameter a equal to 0, you will always get hill type behavior with negative sign. So it's like a what's it called, a concave behavior at A equal to 0. And that can be explained using this Q deformed oscillator picture as well. So the question, actually now, the interesting question that one needs to try to address is, how can we classify all these measure factors, which on averaging gives rise to local unitary theories? And in particular, what do locality and unitarity mean from the Q oscillator side? Okay. Now, this problem here has a name in mathematics. So if I tell you that you classify for me all the measure factors such that this constraint is satisfied, this is called the Hausdorff moment problem. So this is something that we are looking at with Prashant, and we are also talking to some mathematicians in IISc, Apurva Khare and his postdoc. And there has been a recent discussion about this in the fixed T context by Yutin Huang and collaborators. So this is a Hausdorff moment problem, because the Hausdorff moment problem says that suppose you're given this object, there's some probabilistic measure factor, and then you're taking the moments of these, and you're given the right-hand side for all n. Then under what circumstance can we find a unique measure factor here? And depending on the domain of integration, you will get different kinds of moment problems. There are what are called Hausdorff moments, Stieltjes moments, Hamburger moment, and trigonometric moment. Because of the fact that the integration domain is finite, it gets mapped to what is called the Hausdorff moment problem. And the Hausdorff moment problem has a solution. It tells us that if you give me Pn, then for mu to be unique, the solution exists if and only if these Pns are completely monotonic. And this completely monotonic means that these finite differences of these Pns should all be positive. And of course, you can check it explicitly using the type 2 string example, but what additional information you get for general theories is something that we are investigating currently. So I think I'll stop there. So I'm sorry I sort of went over time, and also I had to rush over the end, but if you want to ask me any questions regarding this last part, I'll be happy to answer.
Let's thank Aninda for a very interesting talk. Questions?
Regarding that issue with integrating over Alexander polynomials, don't you ever integrate over Jones polynomials in any way?
This, I think Rama will be in a better position to answer than me.
Yeah.
Right now, he has only done the Chebyshev polynomial related to Alexander polynomial. I don't think such relations, he has just exploited that to write, as far as I see. Jones polynomial is much more, Alexander polynomial is a very weak invariant. If you take two disjoint knots, it's going to be 0. So I don't know how this can be extended.
Rama, his question is a bit different. So his question is that, do we ever integrate over the knot parameter that appears in the Jones polynomial in any calculation?
We are interested. See, integration over knot parameter is equivalent to integrating over the coupling constant in a field theory. We are doing a field theory with a specific coupling constant.
Yes.
We are not integrating over the coupling constant.
Yeah,
so
exactly. So this is like averaging over theories. This is like averaging over theories.
Yeah, so you are taking a Chern-Simons with coupling constant k and integrating over all possible coupling constant going from 0 to infinity. And I don't know what is the meaning of it in a field theory context.
Right.
Well, it can have some meaning in the context of random matrix theories where you integrate over ensemble average. I mean, this is just a statement which has nothing to do with what your talk is about. But I'm just making a statement that ensemble averaging can be done by integrating over coupling constants. That's all I'm saying.
See, we do average, but we do average where expectation value is over the fields in the theory, but not over the coupling constant in the theory. Right. He seems to do it like an average on the coupling constant in the theory by saying he's taking all possible values of Q.
Yes, so you're averaging over theory in theory space.
So for instance, in the SYK model, you average over the coupling constants, right? With a certain measure factor. In the SYK model, you average over the coupling
Exactly.
constant.
No, that is correct. So in that sense, we are averaging over in the theories, over a class of theories or whatever. Yeah.
So it can be interpreted as some sort of ensemble average that is done in random matrix theories or some sort of. You may explore that if you want.
Yes. Yes.
I see.
Yes.
Yeah, and then the information about the coupling is gone then. That's what you mean, right?
That's
like
right.
If you're doing a gravity theory, if you integrate over all possible metric, then you make it metric independent by trivially.
That's right.
In some sense, you are trying to normalize the information about couplings by integrating over all possible couplings.
Yes,
information is not fully gone. You have the average value of the couplings. Or for instance, in the SYK, you have the average value of the J, the coupling parameter.
Yeah, but
that's
depending
not
on the observables, yeah, I agree in some sense, but it is like it's not coupling constant dependent. That's all I meant. If you integrate over all possible coupling, the result is going to be.
It's dependent on the average value.
Correct.
Dependent on the average value.
Yeah, it will be dependent on some. Yeah.
Yeah, but that will be different for different nodes.
Yeah. Yeah. So the amplitude is not going to be as like the correct statement is that the amplitude is not going to is going to be some physical picture where you don't have a rigid knot. You're supposed to think of where
Knot is rigid. Knot is rigid.
No,
You're
but
not changing.
But in order to make the connection with the amplitude, you're supposed to think of the knot as being in some fluid medium or something, where actually
knot is rigid. The invariant associated with the knot is dependent on a coupling constant, which is like ensembles of so many such theories. That's the way you're looking.
Okay. Yeah.
So it will still have the trefoil information on an average value of k, maybe. I don't know. That's the way I think it will be.
Okay.
On a related point, I mean, you can always average, you can always integrate over the knot parameter. But if you suppose you didn't talk in terms of Alexander polynomials, but as Ashok was saying in terms of Chebyshev polynomials, then there would have no problem like this, right?
True, but then I want to interpret the S1 prime integral in the dispersion relation. I could have still talked in terms of this harmonic oscillator, the Q-deformed harmonic oscillator, even if I work with the Chebyshev polynomials, and then it would have still given me the same picture that I'm integrating over theories, right? So here I did not, in order to introduce this, I did not really require to talk in terms of knots.
No, in terms of the Chebyshev, suppose you have the Chebyshev polynomials instead of the Alexander polynomials.
Yes, here.
Then there is no problem in interpreting the integration over the parameter of the Chebyshev polynomial, right?
I mean, in the sense that if I use the map to the Q-deformed oscillator, then again it's the same.
If you didn't use that map, I mean, you use that map to reinterpret your discrepancy, right? So if you don't have the discrepancy to start with, maybe you don't need to reinterpret it in that way.
Yeah, I mean, you could have. I mean, it's not art in the sense that I could have rewritten it in terms of this by just looking at the dispersive kernel, right? So the map exists. So in terms of this map, I'm interpreting.
Yeah, the map exists, but you won't need the map in the case of the Chebyshev. That's what I'm saying. Because it's not necessary. I mean, it's not necessary to reinterpret it in terms of a Q-deformed harmonic oscillator.
Well, I mean, if you wanted to ask the question in a slightly different way, that I want to interpret the integration over the S1 prime variable.
Yeah, that's what I'm saying. I mean, the integration over the Chebyshev parameter, the parameter in the Chebyshev polynomial, that is not problematic, as you were saying.
I mean, if you look at this expression, I said that this is the kernel that you would get for the phi cube theory. And then I'm integrating over this S1 prime over S1 prime, which is the same thing as psi. So I could have looked at this expression. I could have said that this is like integrating over phi cube theories. So you could have asked, what does that mean?
Yeah.
So at the level of the dispersion relation, also you have the same question. that what does integrating over phi cube theory mean?
What is xi here? Xi is it related to the coupling constant?
So,
It's related to just the scattering parameters, right?
It's related to the just in terms of the scattering parameters.
Yeah, so it's not related to the coupling in any way, is it?
No, but in some sense, what you're doing is, so in the phi cube theory, this integrating variable was in terms of mass. So if you see this formula here, I have m squared in the denominator, whereas in the dispersion relation, I have s1 prime in the denominator. So it's as if you're integrating over the masses.
Okay.
Yeah, so you could have asked that, what does that mean?
But this should be a problem with dispersion theory per se. I mean this problem.
I agree. It should be there even in the fixed T dispersion relation. This kind of question you could ask.
Yeah, I mean, if you have to express your crossing symmetric dispersion relation in terms of an integral, this problem will always crop up, right?
Yeah, I agree with that. Except that in the fixed T dispersion relation, we don't say, or we don't try to interpret it in terms of integrating over some known theories. So we don't talk in that language because it's not obvious how to talk in that language.
Okay.
Yeah.
Okay. I have to leave now.
Okay, Rama, I'll catch you on Thursday. Yeah.
Yeah. See you. Bye.
So if there are no further questions, let's thank Aninda again.
Thank you.